Welcome to EDU World Space.
All right, so we're looking now at problem 94 in chapter 22. And what we're asked to do is go to Appendix C, and then we want to calculate the equilibrium constant for equation 22.22 at 298 Kelvin standard temperature. So first, let's write out equation 22.22. We have 3O2. We're assuming no electrical input, but I'm going to write the equation as it's written. Goes to 203. And then we're given the enthalpy of this. Okay, so if we go to Appendix C, the delta G of formation for ozone is 163.4 kilojoules per mole. Now, in this reaction, we're forming 2 moles, so we're going to have to multiply this by 2. But we'll be doing that later. So we've got our free energy change. And now we need a relationship between the free energy change and the equilibrium constant. And the one that we'll use for that is that delta G standard equals negative RT ln of KEQ. And we'll just rearrange this guy. We'll multiply these two terms, the ideal gas constant and the temperature over. And then we'll take the exponent of both sides. So finally, we arrive at negative e to the negative delta G standard over RT is equal to e to the natural log of KEQ, or is equal to KEQ. Okay, so we've done all the algebra that we need to do. Now we just have to make sure that the units in this exponent are correct, and we're inputting the correct delta G values. So for this reaction, we have 2 moles of ozone, so we'll multiply this by 2. So these oxygens are in their standard states, but the ozone is not. So we need only, so the delta G of this reaction is just 2 times the ozone. And we'll want to convert that into joules. So that means that we've got 326,800 joules is the delta G standard of our reaction. And that's what's going to go here. The ideal gas constant that we'll use for this, 8.314 J per mole, okay? Joules per mole Kelvin. And we've got our temperature of 298 Kelvin. Okay, so combining all of those things, just whip out our handy dandy calculator and calculate KEQ. And in scientific notation, we get 5.189 times 10 to the negative 58, which is very, very small. And so the implication here is that because this is very, very small, the energy required to kickstart this reaction is very high, which makes sense because this is essentially a reaction catalyzed by oxygen being struck by lightning. And so this result actually does make sense. This reaction does not favor reactants without the input of energy, and we can see that by the equilibrium constant as well as the very high free energy of reaction. Okay, I hope that was helpful to you.